So I actually think this is going to be the last of the electrolysis videos, a momentous moment, and in this one we are going to look at the electrolysis of brine and what actually brine is and how we use the products from the electrolysis reaction. So look at these two wonderful maps. The reason I'm so passionate about the electrolysis of brine is because this is my home county, and there are towns here that are essentially were founded on the mining of salt. I grew up in this wonderful place here, Tarpley, and to the east of Tarpley you've got towns like Northwich, Middlewich, here's Nantwich, Winsford as well, which were all based on salt mining and the industry that was a knock-on from the mining. You can see that the towns, or three of them here, and actually there's a little part of Northwich called Lethwich, the wich at the end of their name means salt in Old English apparently. And so this county, which is in the northwest of England, look at that wonderful place, much of it is, or sort of grew up on salt mining. There's even, oh, this is an exciting day out, a salt museum in Northwich. You can imagine what a thrilling school trip that would have been. So, what actually is brine? Well, brine is the aqueous solution of sodium chloride. It's salt which has been dissolved in water. And so this is really about what we do with that salt water which has been pumped out of these salt mines under the ground in Cheshire. Here's what the electrolysis cell would look like roughly. In here the brine flows and it would be pushed through the cell and there'd be an outlet on the opposite side. And between the anode and the cathode we have a porous membrane. Now we need the porous membrane because our two gaseous products, A and B, actually react. So we need the porous membrane to stop the two gases from mixing and therefore reacting. So at the top here we have sodium chloride aqueous solution going in. Now, because it's an aqueous solution, we have sodium chloride and water. So we have two positive ions present in there. We have sodium and we also have hydrogen from the water. Hopefully you remember this from an earlier video. And our negative ions, we have chloride and we have hydroxide. Now at this point, if you've watched the earlier videos on predicting products of electrolysis, hopefully you're au fait with the fact that when we're looking for which of these two would form at the negative electrode, we're looking for the least reactive. Okay, hydrogen is less reactive than sodium, so what happens in our cell is that the little hydrogen ions, H plus here, are attracted to the negative electrode, and when they're there they pick up an electron and form a hydrogen atom. Now hydrogen atoms don't usually float around on their own. Okay, so you can imagine you've got one hydrogen atom forming next to another hydrogen atom, so those bond together to form a hydrogen molecule, and this floats off as a gas coming out at B. So hydrogen is formed at the cathode. So the cathode half equation looks something like that. Now hopefully you're thinking, hang on a minute, that equation isn't balanced. You've got two hydrogens on the right and only one on the left. Well, that's easily fixed. put a large 2 there. And again, you're checking yourself, so you're thinking, well, are the charges balanced? Well, on the right hand side, we don't have a charge. But on the left hand side, we have 2 positive charges and 1 negative charge. So overall, we have 1 plus. So it's unbalanced. So we need another negative charge over here. 2 net positives, 2 negatives cancel each other out, so they're neutral, which is exactly the same as what's on the right hand side. So that's what's going on at the cathode, and we produce hydrogen gas. Now hydrogen gas is incredibly useful. Okay, it can be used as a fuel. Okay, it can also be used to make margarine in an organic chemical reaction. I'm not going into the details of that now, but those are the 2 uses of hydrogen that you need to know. So, what's going on at the positive electrode? Well, you've got a choice here between chloride reacting and hydroxide reacting. And if you remember from the earlier video that we said if a halide was present, that would react to form the halogen. So your Cl- ions in there are attracted to the anode, and Cl- would become Cl, and it would kick an electron out. Now, chlorine doesn't go round on its own. It's a diatomic gas, so it would be Cl2. So we'd need 2 Cl's over here, and as the left-hand side had 2 negatives, the right-hand side can be balanced if you make 2 negatives there. So, coming off at A is chlorine, and that's why the membrane is needed, because chlorine and hydrogen, chlorine here and hydrogen here, would react together if given half a chance to make hydrogen chloride, and we don't want that. And we don't want that because chlorine by itself is very, very useful. We can use chlorine to bleach paper. We could, oh, I'm not quite sure, I've pressed the wrong button there, but yeah, we've used chlorine to bleach paper. We can turn it into bleach, so we can make bleach with it. Okay, and we can also make PVC with the chlorine. So, these are 2 of our products, the chlorine and the hydrogen. Now, let's go back to the ions. We can see that chloride is reacting. So, the chloride in the solution is disappearing. The hydrogen ions in the solution are also disappearing. So what we're left with is a solution of sodium hydroxide. So what comes out at C is sodium hydroxide solution. And you should be familiar with sodium hydroxide in the lab. Sodium hydroxide is a very strong alkali. Okay, and it's an alkali because in water it produces hydroxide ions, and so it has a pH of much greater than 7. Okay, it's probably above 11. So not only does this process produce hydrogen, it produces chlorine, it also produces sodium hydroxide, and sodium hydroxide is also incredibly useful. Sodium hydroxide can be used also to make bleach. So what companies do is they take the sodium hydroxide and they react it with the chlorine that you produce here to make bleach. You can also use sodium hydroxide to make soap by reacting it with fats. So you can see this is a wonderful process because you're producing such important products from something quite straightforward, salty water. So back in Cheshire, all they used to do was flood the mines with water, pump out the water which had salt dissolved in it, and then electrolyse it, and you get these wonderful products coming off. Now this was as far as the first edit of the video got, and having watched it back, apart from the ramblings about Cheshire, which are probably not examined, I probably should have also mentioned, or probably the Cheshire bit was probably maybe not worth mentioning, but it was clearly of interest. I should have just mentioned something more about this barrier here. I didn't really talk about it being porous. I said the barrier was needed to stop the chlorine and the hydrogen from reacting, but the wonderful thing about the barrier also is that it's porous, and porous means that liquids can flow through it. So the barrier stops the chlorine and the hydrogen reacting, but it also allows the solution to flow through. And I hope that has proved useful in looking at the electrolysis of brine. If you're ever in the northwest of England, the Salt Museum in Northwich is an absolute cracking day out, and you could continue the tour by going up to the Wirral Peninsula just opposite Liverpool, where there used to be some wonderful soap factories, and that's actually where the wonderful football team Tranmere Rovers play their home games, and that certainly is an entertaining afternoon out.